Hello everybody and welcome to this video where we're going to look at how we can calculate the potential and kinetic energy of a roller coaster. It's over here. As it goes through three different stages, which is the first stage is at the top of the roller coaster, the second stage is in the middle of the roller coaster, and the third stage where the roller coaster is at the very bottom. So knowing this, we can begin our exercise. So calculate the potential energy when the roller coaster is at the top. So we use the simple potential energy formula, PE equals mgh. And we already have the mass of the roller coaster. It's right here. So the mass is 500 times the gravity, which is 9.8, times the height, which happens to be 10. And we plug these numbers into our calculator and we get 49,000 joules. Now remember, gravity in this situation is not negative. We used to make it negative when we were in kinematics, if you remember from the previous section. But given that potential energy is a scalar quantity, not a vector quantity, so we only include gravity as a positive value because we care about what the positive potential energy is at this particular height. So, knowing this, we can move on. Calculate the potential energy, the kinetic energy when the roller coaster is at the top of the track. So, given that we have assumed that the roller coaster is not moving at the very top, it just kind of slightly drops downwards and accelerates downwards due to gravity. So at the very top, there is no velocity. So that's why we can directly assume that kinetic energy is 0 joules. If you want to use the formula, you can. You can tell me it's half mv squared. And given that the velocity is 0, then that means that the answer itself is going to be 0 joules. Next, calculate the potential energy when the roller coaster is in the middle of the track. So now things have changed. Now the roller coaster is falling down. Given that this potential energy, when the roller coaster was at the top of the roller coaster, this was basically the mechanical energy. It was the total energy of the roller coaster itself, which means that now that we're falling down, the potential energy itself should start dropping downwards. So we're going to see how this is reflected mathematically. So we know now that the height is 5 meters. So we're going to use that in the same formula as before, PE equals mgh. M is the same as before, it is 500 kilograms, times the gravity, which is also 9.8, times the height, which happens to be 5. And this time we're going to get an answer of 24,500 joules. And this makes perfect sense because this and this are, basically this is half of the value up here. So, moving on, we can look at question number 4. Calculate the kinetic energy when the roller coaster is in the middle of the track. Now, we don't really know the velocity of the roller coaster when it's in the middle of the track. So we need to remember another formula. So when you want to try to use the formula kinetic energy equals half mv squared, you're going to notice that, oh my god, oh no, we don't have the velocity. So you cannot use this formula. So we're going to use the other formula, which is that mechanical energy is equal to potential energy plus kinetic energy. So knowing this, the kinetic energy, basically we rearrange the formula, we bring the potential energy to the other side and we make it a minus, we flip its sign. We are going to get that the kinetic energy is the mechanical energy minus the potential energy. And what this essentially means when we plug in the numbers is that from before, so the mechanical energy, you get it from before, from this value over here, because remember, at the very top of the track, the total energy, the mechanical energy, is going to be equal to the potential energy. So this is the mechanical energy itself, because this is the total energy. So we're going to use kinetic energy is equal to the mechanical energy, which is 49,000 joules, minus the potential energy, which we just calculated over here, This is quite annoying. There we go. So this is the potential energy. So we're going to plug in this number here, so 24,500, and we're going to get a not surprising number, which is 24,500, which makes perfect sense, joules, which makes perfect sense because, again, the potential energy is going to be divided between the potential energy and the kinetic energy, given that the roller coaster now is in the middle of the track. So, moving on, calculate the potential energy on the roller coaster at the bottom of the track. Now, given that the height, so if we remember here before, it said that the height is 0. Given that the height is 0, that means when we want to apply the formula PE equals mgh, the height is going to be 0. So this means the entire equation goes to 0 joules. And this makes, again, perfect sense because all of the energy that we had before, all of the potential energy that we had before at the top of the roller coaster now has turned into pure kinetic energy. So of course we're going to have a potential energy of 0. So here we can calculate the kinetic energy just like before. We will say that it's the mechanical energy minus the potential energy, and we know the mechanical energy. We know that the mechanical energy from before, it is the total energy that we had. And this is the same always. Once you calculate the mechanical energy, it's always the same throughout the problem. Unless, the problem is telling you extra energy was added somehow, or someone pushes something even harder. But given that this is the same problem within the same scenario, the mechanical energy is still 49,000. So that is minus the potential energy, which is 0, so we get 49,000 joules as the kinetic energy. Finally, we get to the last question, which is the most interesting one, really. It's just to calculate the velocity of the roller coaster at the top, in the middle, and at the bottom of the track. So let's begin with the top and try to calculate the velocity there. So at the top, we remember that the kinetic energy was 0 joules. So this automatically means that the velocity was also 0 meters per second. Because if you don't have a velocity, you don't have kinetic energy. Next, we look at the middle of the track, and we realize that the kinetic energy, or we remember that the kinetic energy was 24,500 joules. And this is based on this exercise right here. So knowing this, we're going to use the formula half mv squared. So we're going to manipulate this so that we can get the velocity. So the velocity, let's start with velocity squared, it's going to be twice the kinetic energy all over the mass. Sorry, this is without the square root. So when we want the square root, we're going to get that the velocity is the square root of twice the kinetic energy over the mass. Okay, now that we have the formula manipulated, we're going to plug in the numbers. So we're going to get 2 times the kinetic energy, which is 24,500 all over the mass, which is, as we said before, what was it? I think it was 500. There we go. All over 500, and we put this number on the calculator. This is going to take me a moment. We will get 9.9 meters per second. Next, we're going to look at the bottom of the track, and we're going to remember from the previous exercise that the kinetic energy was 49,000 joules. So we will see that 2, 3, there we go. When we plug in the formula half mv squared, we're going to do the exact same thing as before. We're going to see that the velocity is the square root of 2 kinetic energy over the mass. So we plug in the numbers, 2 times 49,000 all over the mass, which is 500. We're going to get 14 meters per second. And We would think, so this is something important to note, we would think that if the kinetic energy is doubling, so here at the bottom it is double than the energy on the top, then that must mean that the velocity should also double, but that is not the case. We see that the velocity doesn't necessarily double. It went from 9.9 to 14, so in fact it didn't even get close to doubling. It was just added by around 4 meters per second. So this is basically the idea. We are able to calculate the velocity using the potential energy and the kinetic energy formulas. And then, weirdly enough, or interestingly enough, that can be used by looking at other problems through kinematic equations. So now, in a sense, you have a velocity, and this can be used in a kinematic equation, assuming, for example, that the roller coaster accelerates or decelerates. So more questions can arise if we want to link it to kinematic equations. So that is all for this video. Keep in mind that I might not necessarily ask you this many questions for one scenario. What I might do, or what the type of questions you might get on a test, is I might ask you question number 1, then I might ask you question number 4, for example, and then I might ask you question number maybe possibly 6, and then 7. So I might not get you all of these questions, but it's nice to see how we can solve each and every one of these.